In this video, we're going to look at work energy problems related to rigid bodies. And recall, if the work energy equation is given this way, kinetic energy plus the work done from state 1 to state 2 equals the final kinetic energy. Now, if you have rotation about a fixed axis, the kinetic energy is given this way: 1/2 the mass times its linear acceleration, and this would be the linear acceleration of g, which would be its center of gravity, plus 1/2 the mass moment of the center, about its center of gravity, times the angular velocity. Now, if the mass moment is calculated about its axis of rotation, then this equation simplifies to simply this: 1/2 let's say O is the axis of rotation. Omega squared, or T is 1/2 I instant center omega squared, like this. So again, this would be the case that the mass moment is calculated about the instant center. Now, if you have translation and rotation, we'll have to use this equation up here. Like this. And now, if we have our work, recall the various types of work that we have. We have the work of a moment. And again, so you'd have the moment times the change in your angle, and this would have to be in radians. Now, if the moment is not constant, we'll have to do the integral. So again, this would be if the moment was constant, use this. If it varies with respect to angle, it's this. And then the work of a force. Remember, the work of a force is just the work times the component. Excuse me, it would be the force along the path of the motion. So let's say it this way: work of a force and again, this would be the force along the path of motion. And 3, the work of a weight. That would be like your weight times the change in height, the change in vertical height. Remember, all you have to do is consider how much it's changed vertically for this. And remember, it'll be positive if weight moves downward, and negative if weight moves upward. Next, the work of a spring. Is given by this. Remember, K is a spring constant. No, excuse me, this should be S1 here. So again, remember, K is a spring constant. And like say S2 would be the length it is stretched from the unstretched position. So this would be S2. Remember that it'll be the amount it is stretched from the unstretched position. So if the unstretched position, the unstretched length, for example, is 1 inch, and the spring is stretched to 3 inches, then this will be 2. Or like say over here, if this original unstretched length of the spring is 1 inch and it's stretched to 5, then this will be 4. So these S2 and S1 are the differences from the unstretched position, the unstretched length of the spring. And also, by the way, up here, this S2 and S1, this would be like your final distance minus your original distance. It'd be like how far you've moved along the path. So now let's take a look at some problems. So let's take a look at this problem. The wheel is made from a 5-kilogram thin ring and 2-kilogram slender rods. If the torsional spring attached to the wheel's center has stiffness 2 Newton per meter per radian, so that the torque of the center of the wheel is given by M equal 2 theta, where theta is in radians. Determine the maximum angular velocity of the wheel if it is rotated 2 revolutions and then released. So one thing nice is that we can break this down into parts. We can have our thin ring and our 2 rods. And so our 2 rods, again, they're each 0.5 on each side. So each rod is 1 meter long. And one thing very nice is that, again, when you put these back on the wheel, the rods are both centered about the axis of rotation, and so is the wheel. So we're not going to have to use a parallel axis theorem at all. But we do need the mass moments of these parts. And so the mass moment of a thin ring is given by this equation here, I equals mr squared, where r is the radius of the disk. And up here, we see the mass moment of the slender rod is given by this equation. So we can write those down. This was 1/12. And so now for the ring, we'll have I equal, and then the mass of the ring is 5 kilograms. And the radius of 0.5 meters squared. So we calculate that, we get the mass of the ring. Is going to be 1.25 kilogram meters squared. And then the mass of the rod, mass moment of the rod, and we're going to have two of them. And again, they're both centered about the center rotation, so we can just multiply them by 2, 1/2. And would we say each of these was 2 kilograms? And the length was 1 meter. And so this ends up being 412, basically 2/6 or 1/3. Or 0.333 kilogram meter squared. And so the I total, once again, because everything was, all the centers of gravity coincided with the center rotation, our total, we don't have to include any parallel axis theorem. And when we add these together, we get 1.5833 kilogram meters squared. And then the only work is going to be the work of that spring. And it actually sort of defines it for us. It's going to, that spring is going to result in a moment. Now notice again that the moment is variable. So our moment, as it's given here, is going to be 2 theta Newton meters. So it's going to vary depending upon the angle. So when we calculate our work, the work, again, it's only going to be of that spring or maybe that moment, is going to be the integral of 2 theta d theta. And now we want to know what's going to happen after 2 revolutions. So remember then 2 revolutions would be 2 times 2 pi. So it's going to be 4 pi radians. So this is going to go from 0 to 4 pi. Of course, we're going to get that, we're going to get a square divided by 2. So just leave us with the square from 0 to 4 pi. And that'll leave us with 4 pi squared, which is 16 pi squared. And T1, initially 0 velocity. T2 is 1/2 I omega squared, 1/2 or 1.5833 omega squared. Again, remember, we want our initial kinetic energy and our final kinetic energy. And this is just going to be 0.792 omega squared. Then put everything into our work energy equation. So again, our only work was the work of this moment. We started at 0 angular velocity. So the original kinetic energy 0. Final kinetic energy calculated up here. Put everything in and take the square root, and we get omega to be 14.12 radians per second. Next, we'll take a look at this problem. We have a pendulum with a 10-kilogram uniform disc and a 3-kilogram uniform cylinder rod. It's released from rest in the position shown to determine the angular velocity when it rotates clockwise 90 degrees. So we have a rod and the disc. And so we'll have to take the mass moment about each of those. So for the slender rod, we have this. And so this is going to be 1/12 the mass times the length squared. And then for the uniform disc, we have this up here. It's going to be 1/2 mr squared. Again, now be sure to note if you're given the radius, if it's a solid disc, you're given the radius, then use this equation. Sometimes you're given the radius of gyration. In that case, if you're actually given the radius of gyration, you use that other equation down here, which is like I equal mk squared, where k is the radius of gyration. But in this case, we're given the actual radius of this solid disk. So let's go ahead and calculate these values. So again, for the rod, give me 1/12 times 3 kilograms. (2 meters squared). And when you put that in your calculator, actually, this ends up being 4 times 3. So we're going to have 1 kilogram meters squared for the rod. Actually, this disk is 0.8 meters. I said earlier it was 8 meters. Actually, 0.8 meters. The disk here is 0.8 meters. And so again, the mass moment of the disk is 1/2 the mass times radius squared. So it's going to be 1/2 10 kilograms, 10.4 meters squared. And this comes out to be 0.8 kilogram meters squared when you put everything into your calculator. And that makes sense because this is, when we square this will end up being 0.16. Divide that by 2. That'll be 0.08 multiplied by 10 gives us this. Now, the one thing we have to keep in mind is this time, these mass moments are not about the center of rotation. So what we actually have, so the picture we actually have is looks something like this. And again, the mass moment of the rod is going to be like 1 meter about the center of rotation. I guess they're calling the center of rotation in this problem A. So it's going to be 1 meter. Then the disk, again, this has a radius of 0.4. So its center of gravity is here. So that means the distance from A to that center of gravity is going to be 2, the total length of this, plus the radius, which is 0.4. So this one is going to be 2.4 meters to that center of gravity, like that. So we're going to have to use the parallel axis theorem this time. So if we want to say the total mass moment about A will be the rod, which is 1 kilogram meters squared, plus using the parallel axis theorem, it will be its mass times the distance from its center of gravity to the center of rotation. And we'll square that. That's going to be for the rod. And then for the disk, we have that was 0.8 plus its mass, which is 10 kilograms, times the distance from its center of gravity to the center of rotation. Like that. So mass moment for the rod, using the parallel axis theorem to get it about the center of rotation. Mass moment of the disk, once again using the parallel axis theorem. And this all comes out to be 62.4 kilogram meters squared. Now we're going to have to look at the kinetic energy. So let's look at the two states that we have. We have when theta equals 0. Again, the rod and the disk going to look something like this. Again, where the center of gravity of the rod is here. Center of gravity of the disk is here. Then we're going to have when theta is equal to 90 degrees. Again, remember this is A. And this is state when it's 90 degrees, remember, or pi over 2. So let's think about this. Of course, at the beginning here, there's no velocity. So at the first state, the kinetic energy is 0. And now at the end state, we can say we can actually use this equation because we've calculated our mass moment about the center rotation. And again, what did we call this before? I guess I called it total or T, but it's the mass moment about A. And so we can use this equation. And that's simply 1/2 62.4, I believe we got, times omega squared. So T2 is 31.2 omega squared. Then now we'll have to look at the work that we have here. So we have the case where the moment is applied of 30 Newton meters. So when we consider the work, the work of the moment is going to be, again, remember the moment times the angle, and that was 30 Newton meters times, again, it's had moved pi over 2. And this ends up being 15 pi Newton meters. Now the work of the weight, we have to be careful here. So the work of the weight, so let's consider the rod here. So its center of gravity, let's call maybe this the datum line up here. Say that would be maybe our datum line where we're starting. And so this center of gravity, this started at 0, let's say. And the center of gravity of the rod went down 1 meter. So in this case, we're going to have, for the rod, we're going to have 3 kilograms times 9.81. And then it moved down 1 meter. And so again, this was for the rod. Again, it's positive because it went downward. And then for the disc, it was, what do we say, 10 kilograms. And it started up here again at the datum line at 0, and it's moved all the way down here. Its center of gravity moved, it's 1, 2, and then the radius here 2.4. So again, its center of gravity has moved 2.4 meters down. And this was for the disk. And so I think we have everything we need because we have our kinetic energy beginning and end. We have our work done. And actually, I should have calculated all this. When we do this, this all comes out to be 264.87 Newton meters. So now we're ready to use work energy. And that's T1 plus the work done equal to T2. And again, no initial kinetic energy. And all this work done was positive because the moment turned it downward, and remember the weights dropped. So that's positive with work energy. So that's going to be 15 pi 87. And this is 31.2 omega squared. And when you, let's see, end up being omega squared is 10. So omega is 3.162 radians per second is the final answer. So let's take a look at this problem. The wheel has a mass of 100 kilograms and a radius of gyration of 0.2 meters. A motor supplies a torque of 40 times theta plus 900 Newton meters, where theta is in radians. And again, the mass moment is about the drive shaft O. Determine the speed of the loaded car, which has a mass of 300 kilograms after it travels 4 meters. It's initially at rest, at S equals 0, and theta is 0 degrees. Neglect the mass of the attached cable and the mass of the car wheels. Now, one thing to notice in this case is we're going to have both rotation and translation. This time, there's no way to change this. Well, actually, there probably is, but it gets a little bit difficult. There's no way to kind of treat this motion here of this car as being rotational. So we're going to have like a rotation and a translation. So we can start by doing some things right away. So for the wheel, the mass moment is going to be, let me put this over here. The wheel will be 100 times 0.2 squared. Remember, if we're given the radius of gyration, which we are in this case, then we just use mass times the radius of gyration squared, which is going to be 4 kilogram meters squared. And what else are we going to need? We need to find out how far will the wheel be turning. So after the car moves up 4 meters, how far will this turn? Now, so the rotation will actually be S will be equal to the radius times theta. So we know this is moving up 4 meters. And R was actually given as 0.3. And so that gives us a theta of 13.33 radians. So we're going to need that when we figure like our moment, because we're going to need to put theta into our moment, of course. And so let's see, what else preliminary we're going to need? We'll also need to find out how far the height moved vertically. So let's take a look at that. Say this weight here, our car. So it was originally down here, and it's moved up 4 meters. So let me actually make it just this way. So let's figure the car is down here, and it's moved up 4 meters like this. And if this is 30 degrees, then this is going to be 4 sine 30, or this is going to be 2 meters. So when the car has moved up 4 meters along this incline, it's moving up vertically 2 meters. And let's see what else we're going to need. I think that's probably it. So let's calculate our kinetic energy. So again, at the start, nothing's moving. Kinetic energy is 0. But at the end, we're going to have to use that longer equation again, because we don't have just rotation, but we have rotation and translation. So we're going to have to use 1/2 mv squared plus 1/2 I omega squared. Again, this is going to be for the car. And let's actually calculate that. That'll be 1/2. And the car weighed 300 kilograms was the mass. And the velocity we don't know. But we could say this, though. We could say that this velocity is going to be equal to the radius of the wheel times omega. That's actually going to be the velocity. Because again, as this wheel is turning, its outer radius is going to be turning at a velocity of whatever the radius is, 0.3 times omega, and plus 1/2 the mass moment of the wheel times omega squared. like that. And we put this into our calculator. We get 13.5 omega squared for this. Remember, the 0.3 is squared here. And then we get 2 omega squared here. So our final kinetic energy is going to be 14.5 omega squared, like that. So now let's consider our work then. Again, let's do the work of the weight. Again, we have 300 kilograms times 9.81 meters per second squared. Then the change in height we calculated a little bit ago here was 2 meters. It went upward 2 meters. So that's going to end up being negative. So we have to put a negative in front because it went upward. And then when you put all this in your calculator, you get 5886 Newton meters. And again, that should have a negative in front of it. Remember, when doing work energy, it's negative because it moves upward. It moved upward 2 meters. And then we're going to have the work of the moment. Now, this time, again, the moment was not constant. It was at 40 theta plus 900. Excuse me, plus 900. And so you can either put in the equation integrated or integrated here. You can do it either way, d theta. And so now, remember, we determined that the wheel turned 13.33 radians. So we want to find the work of the moment. It's going to be from theta equals 0. Theta equals 13.33. And if we make this theta squared, this would be 20. Theta squared divided by 2 plus 900 theta. Like that. And so the work of the moment, when you put this into your calculator, it's about 15,552 Newton meters, like that. And then use work energy, put all the stuff in. T1 summation U 1 to 2 equals T2. And of course, T1 was 0. We didn't have any motion. And then plus our work here was negative 5886 plus 15,552. And then we determined that our final kinetic energy was 15.5. Yeah, 15.5 omega squared. And when you put this in your calculator, on the left-hand side, you get 623.6, but then you take the square root. You get omega is 24.97 radians per second. But now we want to know the velocity of the car. So again, remember, the car is being pulled by that wheel. And so if the wheel has this angular velocity, and would we say the radius was, I believe, 0.3 meters, then of course, remember, the velocity of the outer perimeter here is always going to be omega r. So the velocity of the wheel is going to be 2497 radians per second times 0.3 meters. And so the velocity of the outer rim of the wheel will be 7.49 meters per second. And again, that's going to be the same as the velocity of the car because the wheel is pulling the car up. So whatever this velocity is of this outer part of the wheel, that's going to be the same as the velocity of the car. And so that's the answer. So let's take a look at this problem. The 30-kilogram disc is originally at rest, and the spring is unstretched. A couple moment of 80 Newton meters is then applied to the disc as shown. Determine how far the center of the mass of the disc traveled along the plane before it momentarily stops. So we have a picture something like this. And the wheel has a moment applied and 30-kilogram mass. And actually, let's calculate something we know we're going to need. Might as well do the mass moment of the wheel. And actually, this is the only object here that's going to have a mass moment. So it's 1/2 mr squared, which would be 1/2 30 times 0.5 squared. And so the wheel, when you put that in your calculator, that comes out to be 3.75 kilogram meters squared. And then, so we're going to have to find out how far, again, the center moves. And so question is, how do we relate the motion of the center of this to the angle? So remember, so let's say the distance, so let me say distance center travels. So you can actually think of it this way. It's going to be D equals R times theta. And if you're wondering where that comes from, let me actually just show you, but kind of just remember this. So in other words, if the wheel is turning theta, the distance the center will travel for any wheel, as long as there's no slippage, will be the radius times theta. And that comes from the fact, so you can think of it this way. So the distance traveled would be, say, the circumference. Now, of course, the circumference of the wheel. Now, let's say it made one total rotation. So the distance would be the circumference if it made exactly one rotation. But let's say it only made a fraction of a rotation. So it's going to be that fraction of rotation. So a whole rotation would be 2 pi. And let's say theta is something less, let's say whatever it would be, say theta's here. Then if it's only theta over 2 pi, so it's going to be, so the distance that center is going to travel will be the circumference times the fraction of 2 pi that the center rotates. And that's going to, and of course, circumference is 2 pi, 2 pi r times theta over 2 pi. So it becomes r theta. So all you have to remember, again, if you want to know how far the center of something, of a wheel moves, again, if there's no slippage, it'll always be the radius times however much theta it changes. Again, theta has to be in radians, of course. So we have this, and so now in our case, we know that the radius was 0.5. So we know the center of that wheel is going to move 0.5 times theta. And so let's see, we have now one really good thing about this problem is that it's starting at rest and it wants to know what's going to happen when it stops momentarily. So we're going to have T1 is 0 and T2 is 0. So that's going to simplify everything. And then the work done. And again, the work of the moment. Again, it's going to be m times theta, though we don't know what theta is yet, though we know that m is 80 Newton meters. Times theta. Now the work of the spring. Now it's initially unstretched, so at this point we don't even have to have anything. And so it's going to be, so we're only going to have one term, so it's a 1/2 k. Usually we put in s squared, but since the amount of deflection of the spring is going to be the same as the distance as this is moved, we can call the compression or deflection of the spring to be d squared. And another thing in this case to notice is that the wheel, it's actually, the moment is trying to make it move in to the left, but the spring is pulling it to the right. So we want to put a negative here, again, because spring pulls against the motion in this case. So this is -1/2. And we said 200 Newton meters of spring constant. And we're going to have d squared. Now, one thing that we've determined up here, that d was equal to 0.5 theta, so we can put that in. And so when we square this 0.5 times 200 times this, we get -25 theta squared, like that. And now I think we have everything we need. And actually, I'm realizing since these were both 0, we actually didn't even need to calculate our mass moment of the wheel, did we? Because I don't think it comes in anywhere. So in case, let's do work energy. And again, 0. And then the work we have here, we have 80 theta minus 25 theta squared. And again, T2 is 0. So let's see what we can do. We can factor out. Let me bring everything over to the right just to make it look nicer. So I'm going to bring everything over right. That'll make this positive. And that would make this one negative. So we can solve this by factoring. So if we take out 25 theta minus 80, take out the theta. And of course, one of the solutions is theta equals 0. That's a trivial solution. And now if we solve this here for 0, we set this equal to 0. We're going to get theta equals 3.2 radians. And then, so if we want to find the distance, we can go back and use this formula here. So then the distance traveled is 0.5 theta, or 0.5 times 3.2, which is 1.6 meters. So that's how far the wheel moves before it stops.